Hello, welcome to this video about heterocyclic chemistry. Here we're going to look at selective synthesis of indoles. So one of the most iconic reactions in all of heterocyclic chemistry is the Fischer indole synthesis. That is the transformation of carbonyl compound and an aromatic hydrazine into an indole. The reaction starts because the nucleophilic hydrazine rapidly condenses with our carbonyl, a ketone, to form an enamine. So the enamine has a specific set of double bonds in a specific order. You can see that what we have is this six-membered transition state with unsaturation at both ends and then a weak N-N bond, sigma bond, at the other end. This has set us up for a pericyclic rearrangement, a sigmatropic rearrangement, whereby the carbon-carbon double bonds get transformed to carbon-nitrogen double bonds, and the weak carbon-nitrogen single bond gets transformed to a strong carbon-carbon single bond. So after this rearrangement, you can see we have broken the aromaticity, but if we regain that aromaticity by pushing the arrows back into the ring and doing intramolecular cyclization to form a five-membered ring, we make our indole framework. The final step is the elimination of ammonia to regain aromaticity. So if we look at this in more detail, we start off with our aromatic hydrazine. That's an aromatic ring with a single bond to a nitrogen, another single bond to a nitrogen, and a ketone. Hydrazines react very rapidly with carbonyls. That nucleophilic nitrogen attacks the pi bond of our carbonyl to make a new nitrogen-carbon bond. And then the lone pair assists with the loss of water. So it goes down, it breaks the carbon-oxygen bond, and then we neutralise that positive charge by losing a hydrogen. It's important to note that this is a symmetrical substrate, so it doesn't matter which hydrogen we lose, but if it's a non-symmetrical substrate, this can lead to selectivity issues. So now we have a system which has this specific arrangement of unsaturation. The two double bonds are held in such a way that the electrons can flow around in our pericyclic process, and it transforms that weak single bond between two heteroatoms to a strong single bond between two carbons. The carbon-carbon double bonds are transformed into carbon-nitrogen double bonds, but in the same process the aromaticity is broken. So we must draw it regaining aromaticity, and with the same set of arrows we can do an intramolecular attack of our nucleophilic nitrogen onto our electrophilic imine to form our five-membered ring that we have in the product. And the final step then is loss of ammonia. So the lone pair comes in and breaks that carbon-nitrogen bond. And then we regain aromaticity in the final indole product. So this is a very reliable reaction, but can suffer in terms of selectivity. That means it could have reacted on either side of the aromatic ring, and it could have reacted on either side of our ketone. In a more modern synthesis, we can exploit some of the palladium reactions that we have seen in the Larock indole synthesis. Now, you should have encountered several examples where palladium undergoes rapid oxidative insertion into a carbon halide bond. So our palladium 0 catalyst oxidatively inserts into a carbon iodine bond, which becomes a palladium 2 catalyst. At this stage, for our Larock indole synthesis, we get coordination of the palladium to the pi system of an alkyne, and then we get carbopalladation. So that carbon palladium bond adds across the pi bond in our alkyne, and it adds in such a way that they both end up on the same side as the resulting alkene. If there's any selectivity, our large group ends up at the palladium end and the small group ends up at the aromatic end. Well, now we have this nucleophilic nitrogen lone pair, and the palladium has a good leaving group in terms of an iodide. So our nitrogen lone pair can come in and form a nitrogen palladium bond, displacing an iodide leaving group. Then the base that we have added in this reaction will remove a proton from our nitrogen, and the 6-membered Palladium cycle will rapidly collapse through reductive elimination. This will regenerate our palladium 0 catalyst and form our 5-membered indole products. Looking at this in more detail, our starting material is a 2-iodo amino benzene, or 2-iodo aniline. And the first thing we do is we have rapid palladium 0 oxidative insertion into our aromatic iodide bond, the same way we've seen in many of our palladium catalyzed reactions. This turns our palladium 0 into a palladium 2 species. And at this stage, our alkyne will coordinate to our palladium, and then the palladium will add the carbon palladium bond across the pi system. It'll add it in such a way that the new carbon bond and palladium carbon bond will end up on the same side as the alkene. And again, if these two R groups on the alkyne are not the same side, the R group that is biggest will end up on the palladium end. We built a system in which there is a palladium with a good leaving group in terms of an iodine, near a nitrogen with a good lone pair, so that lone pair will come in and displace that iodine. This makes a 6-membered ring, which we have seen is a very good size ring to make. Now the base that we have in our reaction will remove one of the protons from our nitrogen, to give us a neutral 6-membered ring, and then finally a reductive elimination regenerates the palladium 0 catalyst and makes that carbon nitrogen bond that we wanted in our indole. In this video we've had a look at two different indole syntheses. The Fischer indole synthesis, a classic mechanism in heterocyclic chemistry, which is the condensation with a hydrazine and a ketone, followed by a 3,3 sigmatropic rearrangement and loss of ammonia. We've also seen a Larock indole synthesis, which exploits the reactivity of palladium, so we get oxidative insertion of the palladium into the carbon iodine bond, addition across the alkyne, and then cyclization and reductive elimination to arrive at the desired product. Thanks for watching. See you next time.